In this lesson we're going to be looking at volumes of revolution and finding the volume using disk method. You'll notice down here we have a function, and the function is this black line here, and it's being revolved around the x-axis. There's actually an x-axis right through the middle there. And then they've drawn a whole bunch of disks. And in order to find the volume, when you rotate this around the x-axis, we have to find the volume of each disk. And of course, we get a more accurate count as those disks end up being skinnier and skinnier. So that's what the entire lesson is about. So let's start off here with just reviewing what we know about a disk. The first thing we should realize is that a disk is the same thing as a cylinder. And for our cylinder, the volume equals the area of the base, which is going to be pi r squared times the height. All right, now typically in our problems, they're not going to be cylinders that look like this one here. They're going to be like this, skinny ones, and we're going to be revolving, say, around the x-axis. So let's consider if we revolve about the x-axis. So if we're revolving around the x-axis, this skinny little cylinder actually has a height of delta x, and we're probably going to have some kind of curve going on here. So I'm going to just, let's say that's my curve. Then this radius right here is the height of the curve, f of x. So volume of one disk, so volume of one disk is going to equal pi. My radius is now f of x squared times delta x. Now, under this curve, maybe I want to figure out a whole bunch of them. Maybe I'm starting here at A and ending here at B, and there's a whole bunch of cylinders. And if I'm going to add them all up, now I have the integral from A to B. Pi is a constant, so it goes out front. F of x squared, and then it's dx, because when this becomes very, very skinny, we call it dx in our integral. So that's what it looks like if I revolve around the x-axis. And now if I revolve around the y-axis, it's very similar. But this time my width here is going to be delta y, and my function is going to be some function maybe that goes like this. And so this distance from here to here is f of y. And so now, if I want to look at the volume of one disk, my volume equals pi. Now it's f of y, which is my radius, delta y. And if I find the entire volume, now I have to give a starting and an ending place, but let's say I'm starting here at A and going all the way up to here at B, and so I've got an infinite number of cylinders. I'm going to do pi, the integral from A to B of f of y squared dy. All right, so you've got the whole lesson here. We're just going to practice a few problems now. So in this next problem, we're asked to consider the area under the graph of y equals x squared. It's sitting right there. And we're supposed to look at it from x equals 0 to 2, which is exactly what's shown to us, from 0 to 2. And then we're going to revolve it around the x-axis to create a 3D solid. Think for a moment, what is that going to look like? All right, let's see if you were right. This is what you should have been picturing in your head, and we've been asked to find its volume. So I want to point out that what's a sample rectangle right here, when we revolve it, becomes our one of our cylinders right here. There we go. And so when we revolve it around the x-axis, we have a whole bunch of cylinders starting from here at 0 all the way to here at 2. And so let's set up this integral here. So we've got the integral from 0 to 2. And recall, we're always working with pi r squared, and in this case, we've got a delta x, so dx. So we're going to put pi out front. Our radius is the height of this, and the height is determined by this function right here, y equals x squared. So we're going to have x squared squared dx. This is pretty simple to do by hand, so let's just finish this out by hand. Um, First I'm going to want to square this, so x to the 4th dx, and pi antiderivative is 1/2 x to the 5th from 0 to 2, and I've got pi over 5, 2 to the 5th is 32, 0 to the 5th is 0, and there's my answer, 32 pi over 5. All right, let's try another one. In this one, we've got a nice picture here. We're told to find the area under the graph of y equals 1/2 x from 0 to 3. All right, so I'm going to be taking everything from here, 0, all the way to here, 3. And let's just draw in one of these. So here's my radius here, and when I rotate, it's going to get this big, and I'm going to end up with a cylinder, something like right there. And I'm going to have a whole bunch of those. Now you might be saying to me, hey, this is just a cone and I know the formula for a cone. And yes, you can check your answer that way, but we're practicing calculus right now, so we're going to do this using calculus. So our integral is going to go from 0 to 3 because, again, each cross section is pi r squared. I have pi. Our r squared, r is this right here because the height from here to here is 1/2 x. So 1/2 x squared, and dx because the width of this is delta x. All right, so let's just get an answer for this. Pi, I need to square this out. So it's going to be 1/4. I'm going to put that 4 here, x squared dx. And that's going to equal pi over 4 times 1/3 x cubed from 0 to 3. See, pi over 4, I put in a 3, 27 over 3 is 9. Oops, didn't mean to put a parenthesis there already. So let's try that again. So 9 minus 0, and I get 9 pi over 4. Okay. So this next one, let's see, is there anything different about this one? Probably just, oh, look at this. We're going from 1 to 2. So it is important to note that we don't always go starting at 0. So from 1 to 2, there's our region. And y equals x squared plus 3. And we're still going to go around the x-axis. So for this one, our region like this is going to be rotated, and we can see if I just draw in one of these, this is kind of where it's going to be, right? We still have delta x, and our radius is this, x squared plus 3. All right, so let's set up our integral. This is going to go from 1 to 2. It's pi times r squared. Our radius is the height up to here, which is the function that was given to me, x squared plus 3 times the width dx. All right, now we could just throw this in our calculator, but it's probably good practice to do this by hand. So let's just get an answer for this. Oops, I forgot to square it here. So hopefully everyone noticed that as I was doing this. You'll notice the pattern here is that we're always got pi, the integral of r squared, d either x or y. All right, so pi, and before I can integrate this, I'm going to have to square this. So x to the 4th plus 6x squared plus 9 dx. So pi, and now I'm ready to integrate. 1/5 x to the 5th plus, let's see, that's going to be 2x cubed plus 9x from 1 to 2. And now we're going to plug in our numbers. So I've got 32/5 plus, let's see, 2 cubed, 8 times 2 is 16, plus 18 minus, plug in 1/5, minus 2 minus 9. And for our purposes, I'm going to leave our answer right there. All right, so let's look at our next problem. This time, notice, and it's in blue for you, what we're revolving around the y-axis. So let's look at the region we're working with. Y equals x cubed, y equals 8. That looks a little different. Y equals 8 is the region, the line from here to here. X equals 0 is this vertical line, and of course here's our curve. So this is the region we're looking at, and let me just shade that in. I guess we can just do the whole thing in purple here. And now we are told that we're going to go around the y-axis. So this is going to look like some sort of a bowl. So let's just draw in one cylinder here. And so this one cylinder is good. Oops, I don't have a very good angle on that. Let's try that again. So that one cylinder is going to go like that. There we go. So there's one of our cylinders, and we can see that it's going to be delta y. And we talked before that this distance has to be a function of y, which means we're going to take this equation and we're going to solve it for x. So x equals the cube root of y. So the distance, remember when we go across, is x, and so x keeps changing because our x distance changes according to the function cube root of y. All right, so let's just mark that. So this distance is the cube root of y because that equals x. All right, so we're ready to write our integral. Our integral now, notice our discs, and I draw these in because we can see how they're going to be stacked. They're not going to be stacked left to right. They're going to be stacked from bottom to top, which means our limits go from 0 to 8. Now we're still working pi radius squared dy. So we need to square that. So we have x cubed squared. We need that pi out front. And we have dy. Oops, I made a mistake. Remember, we said it had to be in terms of y. So let's go back and fix that. If I have dy here, everything has to be in terms of y. So we notice I have y values here, but here I need the cube root of y squared dy. All right, so we've got pi, my radius squared, my width, which is dy, and now we're ready to just integrate. And before we do this one, it helps to rewrite this as y to the 2/3 dy. So we can do the antiderivative of that. Let's see, add 1, we're going to be at 5/3 times 3/5, and we're going to go from 0 to 8. And so we've got 3 pi over 5. And when we put in 8, let's see, the cube root of 8 is 2, and 2 to the 5th is 32. That number has come up a lot in this lesson. Minus 0. And so let's see, it looks like we're going to have 96 pi over 5.